Hello, my name is Ben Letson, and I'm in the Mechanical and Aerospace Engineering Department at the University of Florida. Today I'm going to be talking about the long-term performance of the UV LEDs that we plan to use for the LISA mission. So we're using these LEDs in the LISA charge management system. Unfortunately, I don't have time to go into specifics about what the charge management system is or why we're even using UV LEDs. But if you're interested in learning about any of those two topics, you can look at some more talks from some of my colleagues, Myles, Sam, or Taiwo. So when we started these lifetime tests about a year ago, we had a few main goals in mind. The first of which was we wanted to develop some model for power degradation and look at how different factors such as environmental temperature, drive conditions, and pulsing properties affected the long-term performance of these UV LEDs. And then we also wanted to look at different things such as the electrical efficiency and the pulse shape and see how that affected LED performance as well. So the second goal of our lifetime test was to evaluate the risks associated with different LED operating conditions. So it turns out that we can achieve the requirements of the charge management system by running these UV LEDs in about 6 different operating modes. 2 of these modes are considered high risk because the UV LEDs are on for the entire 10-year LISA mission. So our second goal is to predict the likelihood that these UV LEDs will survive these high risk operating conditions. So the third and final goal of our lifetime test is to develop some sort of screening process that we can put these UV LEDs through so we can make sure that we don't accidentally choose an LED that's going to die mid-flight. So in order to achieve these goals, at the University of Florida, we've put together a test system that can test up to 96 UV LEDs at once. So this test system consists of 12 boxes, and each box can hold up to 8 UV LEDs. Each box acts as its own semi-sealed environment with its own dedicated temperature controller where you can specify the temperature anywhere from 20 degrees Celsius to 80 degrees Celsius, as well as channels to monitor the power output of all 8 LEDs, as well as the voltage response, and specify the current using custom electronics. To analyze the effects of a wide range of operating conditions on 4 different types of LEDs, we first started with 4 different operating temperatures. Then we split that into 2 different modes of current operation, each of which we tested at 3 different stress levels. So if you do the math, that's 96 unique operating conditions, which means that there's only one specific device for each unique operating case. The hope was that by testing a wide range of operating conditions to get an idea for which factors affected the rate of power degradation the most. So remember that I mentioned that there are 2 continuous discharge modes that we're calling high risk? Well, the other discharge modes are called intermittent discharge modes, and in these modes, the LED is only on for about 10 minutes every 4 days to do a high power discharge. So if you look at these modes of operation that we tested around temperatures that you'd expect to find within the LISA spacecraft, all of the LEDs that we tested survive for at least 15 LISA lifetimes. So here you look at a power of relative LED output power over days of operation. So if we consider an intermittent discharge case where the LED is being operated at 100,000 pulses per second for only 9 days spread out over the entire LISA mission duration, the LED that behaved the worst in our test only lost about 30% of its original power. So if you consider the other intermittent discharge case where the LED is being run continuously at an operating current of 20 milliamps, the worst performing LED that we tested only lost about 20% of its initial operating power. Now when we look at the high risk cases where the LED was on for 10 years continuously, we were only able to test for about 190 days, which is about 5% of the LISA mission. But in that time, when you look at the LEDs that were being run in a pulsed manner, no LEDs showed any power loss during the time we were testing them. And then if you look at the LEDs that were being run in a continuous manner, the LEDs lost no more than 10% of their power over that time. Since we were only able to test the continuous modes for a fraction of the LISA mission duration, we need a model to use to predict the degradation over a longer period of time. We could use the standard LED decay model where one decay constant is dependent on temperature and the other decay constant is dependent on drive current. However, because we had such low sample statistics in our first test, it's difficult to predict with any level of certainty at what time the LED will fail. To get a better idea of what the behavior of a larger sample size of LEDs would look like, we used a Monte Carlo simulation to generate a large number of simulated LEDs from the distribution of fit parameters that we saw in our lifetime test and examine the effects of device variability on LED lifetime. So we simulated 10,000 LEDs from the combined fitting parameter spread of 4 different types of LEDs at 20 and 40 C. And then we defined failure as the time it takes for the LED to lose 70% of its initial power. So from the Monte Carlo simulations, we can say with 95% confidence that LEDs being run in a pulse continuous manner will last for at least 8 years, while LEDs run continuously at a low DC current will last for at least 1.5 years without failure. So the big takeaway from our first lifetime test is that UV LEDs will survive intermittent discharge modes without a doubt. And the results for the continuous discharge modes look promising so far. However, because of the small sample size, decay parameter distributions are hard to obtain, which makes accurate predictions difficult. So as we move forward to our next lifetime test, the theme is to test as we fly. And what we mean by that is we want to operate the LED to as close to flight-like conditions as possible. So in the first lifetime test, all of our analysis was based on relative power decay under static operating conditions. In LISA, however, if the LED starts to lose power, we can always either increase the drive current or increase the pulsing parameters to maintain a constant power output. In order to implement this into our second lifetime test, we added a power feedback controller into our test control software. The next improvement we're making to our second lifetime test is we're adding the quasi-DC operating mode, where finer output power control can be achieved through 1 Hz pulse width modulation. This mode also eliminates potential electromagnetic interference by using lower frequency modulation. The last improvement we're making to our second lifetime test is to eliminate operating conditions that we would not expect for LISA. We're only testing one type of LED at a single temperature, and then by testing the high-risk quasi-DC and pulse continuous operating modes, we divide our 96 LEDs into only 2 different cases, meaning that we can now collect proper statistics for further analysis. We already performed a multitude of pre-tests on each individual LED, such as DC spectra and UV output power over 20 different operating currents, current voltage response of each LED to get a better idea of the physical LED semiconductor structure, as well as pulse shape properties at different conditions to identify responsivity and timing for the LED. We've also learned how to better identify device characteristics and physical differences between LEDs. Our hope is to correlate these pre-test results with LED performance during the second lifetime test, which we intend to start this month, and we'll be taking data over the duration of the next 2 years. All right, so that's all I have. Thank you for tuning in. Don't forget to like and subscribe, and if you have a question, just leave me a comment and I'll get back to you. Have a great day.